In this video, we're going to prove two corollaries of the previous theorem. The previous theorem said that if P divides A and B, P is prime. That guarantees that P divides A or P divides B. That's the prior theorem. Now we're saying that if P divides a whole product of integers, then P must divide at least one of them. Okay, so we're going to do this by induction. Okay, so if n is 1, we're doing induction on the number in the product, the number of integers we're multiplying. So if P divides A1, well, P divides A1. If n is equal to 2, that is P divides A1, A2, that implies by the previous theorem, that P divides A1 or P divides A2. And I just want to show that P divides at least one of them. Okay, now we assume for n is less than k, where k is at least 2, we assume that if P divides A1, if P divides A1 times A2, then P divided one of them. If P divides A1 all the way up to AN, then we assume that P divides AK for some k in their interval 1 to n. Integers from 1 to n. Okay, so now we need to show for n is equal to k plus 1 that if P divides A1 if P divides, just troubled about something. First of all, I want to call that L because I'm using A sub k for some arbitrary value. Now, if n is equal to L plus 1, so A up to AL times A sub L plus 1. Well, that clearly implies that P divides A1 times A2 up to AL plus 1. Well, think of that as one number. After all, if you multiply L numbers, you get one number. Never multiply two numbers and get two answers. 7 times 2 is one answer. It's not 14 or 23. Well, that is not true. 7 times 2 is 14 or 23. 14. But it's never both. Okay, so P divides A1 by star. P divides A1 or P divides A1 or P divides that number. A2 up to AL plus 1. but this is only L numbers. So P divides A1, but this one implies that, remember, if N is less than L, P is going to divide one of them. This implies that P divides AK for K in between 2 and L plus 1. Well, that's what I wanted to show, that P divided one of these. Either it divides the first one, or it divides one of the remaining ones. I don't have to show which one it divides. I just have to show that it divides one of them. My job is easy here. Okay, that completes this proof of this corollary. Let's get into the next corollary. This one talks about P1, Q1, Q2, up to Qn. And P divides the product. Then P must divide QK. P must divide one of these. Okay, proof by the previous corollary. If P divides this product, then P divides one of them. P divides QK for some K in between 1 and N. Okay. Now, QK being prime is only, see how I'm going to say that. Is only divisible by only positive, divisible by 1 and QK, positive divisors. Okay. But P being a prime, but P being a prime is greater than 1. Okay, so a number greater than, this is a number greater than 1, and it goes into a prime number. This forces P to equal QK. Okay, it can't be that this here is 2 times P. Okay, P can't go into QK unless P is QK. 7 can go into 14. But 7, if it's gonna go into a prime, it has to be itself. 7 doesn't go into 11, which is prime. 7 doesn't go into 19, which is prime. If a prime number goes into a prime number, that means those numbers are the same. Doesn't go in. But 19 goes into 19, and 19 being prime will not go into any other prime. This implies that P must be Q. If you like videos like this, subscribe to my channel. Click the like button. See you guys in the next video, and as always, watch and learn.